All right, hey friends, what we're going to pick up in this video is we're going to finish up just the stuff from the 2.6 derivatives of inverse function. So we had talked about just inverses in general, and then we have this general formula on how to find the inverse of the find the derivative of an inverse of a function. And it just relies on this fact that the slopes are reciprocal, so we can kind of see that idea of 1 over, kind of like we were seeing up here, like 3 and 1/3. Right, we're just visually getting that idea of the 1 over, so we can multiply to 1, right? That idea of multiplicative inverses. So in other words, if I'm looking for the derivative of an inverse, what I should do is take the reciprocal of 1, or in other words, what I should do is do 1 over and then find the derivative of the original function. But rather than evaluating it at x, we should evaluate it at the inverse of x. So in other words, we did some examples there. What we didn't get to cover was the derivatives of inverse trig functions. And for a moment here, I guess I do want to blanket state that I never want you to use the inverse notation for trig stuff. If you do, it's not wrong and you'll consume it in other places. But if I'm trying to instruct you for success before, what I mean by that is normally if we have a function f of x, that little -1 is the inverse symbol. And yes, it does work for sine, right? If I just think of like the sine of x, this symbol, the inverse sine of x, is appropriate. However, I just tend to find it's wicked confusing, and which is why most mathematicians and why most like textbooks and all this other stuff, we still use this idea of the arc sine. It has some other mathematical definitions, but really I want us to think is as another way, and I'm saying mathematical definitions as to why we think of the word arc, right? We can kind of connect some things with the arc of a circle. But in general, right now, I just want us to associate those two are the same. The inverse sine of x and the arc sine of x are exactly the same. And just as a quick little introduction, like why would this notation even be used and why is it better than this one? I have a quick little graphical representation of that. So right here, this is just the sine of x, right? That's where we're starting. Now we've developed this notation that whenever we're using powers of inverse trig functions, we put them right after the n in sine. So like here in red, you can see sine squared is coming in. Now that notation works for everything. Sine cubed, sine to the 4th, sine to the 5th, sine to the 6th. But it doesn't work for sine to the -1, right? So just to show us, sine to the -1 is the arc sine of x, right? So here, this is the inverse sine with that notation. This is the inverse with our green notation, or our arc sine notation. That's not the same as the negative first power. So I prefer to use the arc sine notation because it tends to not break those rules. All of a sudden, when I put that little -1 there, where all the other powers were supposed to go, now it's not a power. That's confusing to me. So I'd rather just stay away from the inverse, that negative first power, and I would just rather just write it as the arc sine. Now you'll note if I did want to use the inverse, or sorry, the negative first power, I have to put it outside the parentheses. And just so we can see if I do 1 divided by the sine of x, we'll see that those are now actually the same, right? The inverse in blue, sorry, I keep saying inverse, the negative first power in blue and 1 over in green, those are the same. But as soon as I put a -1 next to the word sine, that does not mean the same thing anymore. So that's why just traditionally we tend to use the arc sine. Now, we're not going to prove all of these, but I do want to at least do one quick little proof. And on this one, I just want to prove the arc sine one real fast because it does kind of relate back to our basic understanding of inverses. So these practices here, we're not going to do. These were just regular chain rule practices. We don't need those chain rule practices. But let's say we were trying to like ask ourselves, like in general, what is the derivative of the arc sine of x? Or in other words, if I let a function y equal the arc sine of x, what is y prime? Right, and we can go back and rely on our definition of inverses. So if I say that y is the arc sine of x, doesn't that then, by definition of inverse, mean that x is equal to the sine of y, right? So when we go from that then, if I just start with this statement, let's differentiate both sides with respects to x. I'm going to have to just move that over. So let's differentiate both sides with respects to x. The left side's easy because it is in terms of x, but the right side is in terms of y. So we're going to have to use a chain rule there in our implicit kind of differentiation. So the derivative of sine is cosine of the inside, and I have to multiply it by the derivative of that dy dx there. So then it's easy to get dy dx alone, right? This is just 1 over the cosine of y, which is equal to dy dx. Now, if we just substituted y directly, because we know that y is the arc sine of x, putting the arc sine into a cosine function just pretty much seems uncomfortable. Wouldn't really want to do that. So we could just use this other fact that we know that sine squared of y plus cosine squared of y should equal 1. So then in other words, if I'm just thinking, what is the cosine of y? When I isolate and then I take the square root, which I'm just going to erase the squared and then put in that little square root symbol. Right, the cosine of y can be thought of as 1 minus sine squared of y. But in other words, sine of y squared, well, we said the sine of y, or we said y was, the sine of y was equal to x. So wherever I see the sine of y, I can replace that with x. So if I see the sine of y squared, I can replace this. So instead of the cosine of y, I can replace that with 1 minus x squared. So that's just a general little idea of how we're coming up with some of these proofs. You're welcome to look at more of them if you so chose. But for right now, what we want to gather from this then is that all of these derivatives of inverses are things that we then need to kind of memorize. Their proofs do follow similarly. But for right now, it's okay with us just thinking this is something that we need to memorize, add to our derivative lists. We should now see a huge list of derivatives. I do believe this is probably our last derivative formula that we're going to learn. So we should be able to make like a nice little study guide. So after this point, I just wanted to do a few examples of things on these notes here, as well as maybe a few from the homeworks. So I guess if I was going to choose one to do from the notes just as an example, let's just do, I guess, it doesn't really matter. How about number 5? Just because number 5 has, it has an arctangent in it, I guess. So here we should see this is a chain rule, sorry. So what I can see here is first, I'd have to take the tangent of something. Once I figured out what that was, I would plug that in to the arc sine and ask what the arc sine of that was. So I'm just going to assume that's y. So then if I'm looking for dy dx, or in other words, the change to the output with a small change to the input, I can view this as a chain rule, right? I could do du times dx times dy times du. So the first thing that I would see is the derivative of du with respects to x. The derivative of tangent is secant squared of x. And the derivative of y with respects to u, the arc sine, well, that's one that we just used here, right? The arc sine is 1 over the root of 1 minus that input squared, right? And notice in that formula, the input was x, so then we squared that input. So then here, if we think about the derivative of the arc sine of u, that's going to be 1 over 1 minus the input squared, and that's under the root there. Now, from here, what is u, right? We should do some replacing here. So we have secant squared of x times 1 over 1 minus, and we said u was tangent squared of x, and that's under the root there. So then from here, that's all I want to simplify with that. Secant squared of x over 1 minus tangent squared of x's root. So just we can see a general idea of how we utilize that. All right. If we wanted to do number 4, I guess that's also fine, right? We could think of this as a chain rule. We have this outside function and this inside function. So if I was going to try to do this in a little bit of a different of a way, rather than using like that u and y technique, another thing we could do is say, okay, what is the derivative of the outside function? So the derivative of that outside function, the arctangent of x, the derivative of arctangent of x is 1 plus the input squared, right? Whatever this input was, that has to be squared. And then that input we have to multiply by the derivative because of that chain rule. So here, the derivative of arctangent, so we get this 1 over, and here I'm just separating, putting that as a 1 and multiplying by u prime. We can see that for all of them, right? Like 1 over 1 plus u squared times u prime would be the same thing there. So 1 over 1 plus the input squared. So the input was t squared, and then I would have to square that. And then we have to multiply by the derivative of that input, which is 2t. So when we combine these with multiplication, we get 2t over 1 plus t to the 4th. So just some examples of how we work with those. So that's the end of the notes. I did want to do a few of them from your homework. There's two of them that I wanted to pull out just to get you going for today. Well, actually, I was going to do 3 of them. So the first one I was going to do from your homework. So now I'm transitioning to the homework. So if you need a moment to go find that homework that I've assigned to you, the ones that are circled. The first thing I'm going to do is number 1. And in number 1, the directions are saying verify that f has an inverse. So they give us this function f of x, which is x cubed minus 1. So what we should see here is this function is continuous over its entire domain. So they're really asking us to go back and look at something like this. Like, yeah, it's going to have a continuous inverse. And since that polynomial is differentiable, we should know that its inverse is also differentiable. Now, what we're asked to do is we're supposed to find the derivative of the inverse function at whatever point a they give us. So here they're telling us that a is equal to 26. Now, finding the inverse function of this wouldn't really be too bad. If we think about, undoing a minus and then using a cube root, shouldn't be too bad, but we actually don't ever really need to find that if we're going to just look for this information, right? If I'm looking for the inverse's derivative at a, which in this case is 26. According to the formula, it's 1 over the derivative of the regular function, but this time evaluated at the inverse of that input. So here then what we're really asking ourselves is what is f inverse of 26? What does that equal? And if we think about the inverse, in other words, we're asking what did I plug in to f to give me the output of 26? So hopefully it's not crazy here for us to see that that would be f of 3. And if we didn't know, let's just start trying plugging in some x values. It's not 1, it's not 2, it's not 3. We're going to try to choose some that are fairly easy for you to grasp. We can see here that 3 cubed, 27 minus 1 is equal to 26. So what this tells me on the function, if I plug in 3, I get out 26. So on its inverse, if I put in 26, I would have gotten out 3. So as we come here, then we would change this to f prime of just 3. Well, we can do that because we know what f is, right? F is x cubed minus 1. So f prime of x is 3x squared. So then if we plop in that into our formula here, the derivative of f at 3, well, that'd be 3 times 3 squared, which is ironically 1 over 27. So again, that's kind of the flavor for those that follow after that 3, 5, 7, and 9. So the next one I did want to choose from the homework was something like number 11, just kind of exemplifying that, that process there. So what it wants us to do is show that the slopes of the graph of f and f prime are reciprocals at the given points. So they give us f of x is equal to x cubed, and they just give us this information that the point 1/2, 1/8 is on that line, or that curve, excuse me. And then they give us its inverse, which is clearly the cubed root of x. And then they also give us the information that 1/8, 1/2 is on that line, which would make sense, right? We can see the idea of the inverse flipping the inputs and the outputs. So the question is asking the slopes of the graph at those points. So the slopes of the graph are the derivatives. So they want us to see the derivative at the input of 1/2 of x should be the reciprocal according to the directions, of the slope of the inverse, so that's the derivative of the inverse, at that input, right? Because they said at the points that were given, and we know that everything has to do with inputs. So with this one, f prime of 1/2, that should be fairly easy, right? F prime of 1/2 would simply be equal to 3 times 1/2 squared, which is 3/4. Now coming over here to the inverse, we have to set up our formula. The derivative of an inverse is 1 over the derivative of its function just evaluated at that input of the inverse. So when we think about this moving forward, then we know what is the inverse of 1/8. Well, in other words, what did I put into the original function to get out 1/8? Well, I must have put in 1/2. So then simplifying our notation, what is the derivative at 1/2? Now the derivative of f at 1/2, again, we get the same thing we had over there. This was 3 times x squared, which is 1 over 3/4, which is, of course, 4/3. So we can see that those slopes are reciprocals, right? And if we multiplied them together, we get that classic identity of 1. The last example I did want to go through was number 19. And on number 19, I guess I need another page. I encourage us to do it 2 ways on that. So just copy number 19. They want us to find dy dx. And in number 19, they first give us an equation, x is equal to y cubed minus 7y squared plus 2. And they give us the point -4, 1. So they want us to find the derivative at that point. I might just stop at the derivative and let you put that point in. But again, we're going to do this in 2 ways. And I think the most common way we see it, if we were looking for dy dx, this looks a lot like our implicit differentiation. So we could go ahead and take the derivative with respects to x of both sides. So I'm going to just use some copy and paste here. So the derivative with respects to x, and then we would take the derivative with respects to x on the other side. And on that other side, we can see that, well, that isn't in terms of x. So that's why we have that implicit differentiation going on. So it's a great review of that, right? So the derivative of x with respects to x, that's just 1. Now, as we're doing this derivative over here, we're just going to use that sum and difference rule in real time. So the derivative of y cubed would be 3y squared. But since we're differentiating with terms to x, we'd have to multiply by dy dx. Moving forward, we get 14y using the power rule. But then since we're implicitly differentiating, and then that plus 0, which I'm not going to include. So from there, then, we could just use our factoring. Factor out dy dx. We'd have 3y squared minus 14y. And then just by division, 1 over 3y squared minus 14y should equal dy dx. Awesome. We definitely did it. And if you had to go evaluate that function at the point -4, 1, kind of notice that notation just means we're evaluating this function at that point. We actually don't even need the x value according to that. So you can go ahead and finish that up. But what I wanted us to see is an alternate way of doing it, right? If we're looking for dy dx. Now, what I want us to see here, that x is really just a function of y, right? If I wanted to figure out what x was, I'd have to input a y value. And then once I knew what y was, that'd be wicked easy to do. Just like before, how we see things like y is a function of x, right? So that's why we say it's a function of x. So since we're looking for the change in this output, but it's always defined by that input, that's why we make a small change to x, because the function is defined by x. But here, just erasing my notation for a second, x is defined by a function of y. So wouldn't it make more sense to differentiate both sides with a small change to the input of y? Because again, if I view x as a function of y is the input, and I want to make a small change to my input and see how that affects the output. Now this left side is a little bit weird, right? This is just dy dx, or in other words, we could view this as a chain rule. The derivative of x is just 1 But since we're differentiating with respects to y, we'd have to multiply by that differential term, just like we're doing over here. If I'm differentiating with respects to x, and this is in y, I have to multiply by dy dx. Here I'm differentiating with respects to y, so that the differential term is dx dy. But on the other side, since I'm making a change to y, and these are written in terms of y, that's really easy. I can just go ahead and use my power rule, right? Well, okay, what does that help us do? Well, not a ton, right? We can see that dx dy is 3y squared minus 14y. But where's this inverse stuff coming in? Isn't dx dy the same thing as 1 over dy dx, right? If I just do 1 over, and instead of dividing by dy dx, how would I multiply by its reciprocal? So if I know what dy dx is, then I can easily say dy dx is 1 over that. And we then see we get the same answer, 3y squared minus 14y. So just a nice kind of, in my opinion, nice calculus problem that helps us work on implicit differentiation, but really helps us look at the definition of our derivative. What is the input? What is our small change? And a nice way to think about that, I guess, reciprocal or multiplicative identity with that 1 over. So you should have the rest of your assignment posted on Canvas. Some of it's review, some of it's from this textbook. So hopefully that gets you started. And I hope you have a good day.